All right. Hello, everyone. On the back, can you guys hear me? Garrett, you just walked in. Can you hear me? Good. Thanks. All right. Happy Wednesday. I hope you guys are doing well. Is it Wednesday today, right? Yes, Wednesday. So we will start with the new module in N degree of freedom systems. So on your notebook, when you see these chapter 5 or section 5, this call. If you're taking notes. Okay, so most of vibration courses, I remember when I had this course as undergrad, like the teacher spent out of 40 sessions, maybe 32 or 33 sessions on single degree of freedom system, 2 sessions on, or 2 or 3 sessions on 2 degree of freedom systems, and then 2 minutes on N degree of freedom systems, and 1 minute on infinite degree of freedom system, which is continuous system. And later, when I had this course in like in grad school, like the advanced version of vibration, the same. Half of the course was on single degree of freedom system, then a lot of talking about 2 degree of freedom system, then we switched to continuous system. Anyway, my point is the main concepts, you've learned them in single degree of freedom system. We will discuss 2 degree of freedom system and 3 here. The reason is everything that we teach based on 2 and 3, they're going to be the same for N, and N can be any number. But manually writing the equation more than 3, it's going to be a lot of like work and a lot of pain. And we use computer usually. So it's going to be a lot of focus on 2 and 3 degrees of freedom system in this chapter. And in fact, that's an interesting topic. If the single degree of freedom system in this course hasn't yet piqued your interest, I'm sure this topic will. It's way more interesting than the single degree of freedom system. So speaking of degree of freedom system, I'm sure in your dynamic course before, you are familiar with degree of freedom system. The same concept in vibration. We say when we are in 2D, by 2D I mean, let's say I'm analyzing the motion of an object on a plane, let's say on this table, it has 2 degrees of freedom system. If it is in a space, it has 6 degrees of freedom system. Then we constrain this freedom by some, let's say, structure or other mechanism, and we reduce the degree of freedom system. So, so far you've seen like a particle which we discussed, and it was attached to a spring. So remember, a spring is not going to affect the degree of freedom of a system, right? So a spring just creates some resistance, but it doesn't change the degree of freedom of a system. So this system that we discussed, it was a 1 degree of freedom system. Of course, the mass can move left and right, but we said we are only interested in this problem in one direction. Maybe somehow we constrain the motion of this mass by, let's say, putting it inside a rail or something. But schematically, when we show it, we didn't show these walls. Right? So this mass can have a 2 degree of freedom system, 2 DOF, because we can claim that it can move in X and Y direction. So it can move in X and Y direction, so it has 2 degrees of freedom system. And remember, they are still particles. When they are particles, we don't care about their rotation because they are small. So you may say, no, this particle can move, let's say, on an angle. That's correct as well. However, we can find if it moves, if I have X and Y, I can find its motion on that slope as well. So just 2 variables, X and Y, tell me what's going on for this system. And speaking of vibration, we can constrain the motion of these things. Let's say put in a spring here, a spring over here. So this is now K1, K2, and maybe another spring over here, K3, and another spring at the bottom. So it will be then K4. So now you can imagine there is this mass in the middle. It can move left and right, ups and down, or it can go on any angle. And there are some springs which create some vibrations. So another scenario, now instead of a particle, let's say we have a rigid body. So these are particles. It means the size of them doesn't matter. What if we have rigid bodies? So when we say rigid bodies, then the size of them matters. It means they have mass, moment of inertia. Their rotation also matters. So this bar, for example, it can have 3 degrees of freedom system. It can go ups and down, left and right, and it can rotate. But let's say I'm only interested on its motion when it goes ups and down. Let's say I put it on 2 rubbers, maybe springs, K1 and K2. And I want to analyze its motion, right? So for this, then we say it can have degree of freedom moving ups and down, right? That's 1 degree of freedom. Let's call it Y. And it can also rotate, theta. So it is a 2 degree of freedom system. So you may say it also can go left and right. That's correct. But let's say we are interested only in Y and theta. Maybe the motion on left and right is not that much that interests us. Okay? So imagine if this is a car. You just want to know how much it moves ups and down and how much it tilts. So 2 degree of freedom system. But the question, if the question asks you that you're also interested in the motion left and right, it's going to be 3 degree of freedom system. And eventually, if you have, let's say, a box, and I put it on 4 springs, and 1 spring on the other side. So the degree of freedom for this system, we can say let me put our coordinates somewhere at its centroid. Let's say this is the centroid or the center of gravity. Let's call it G, center of gravity of these things. And I put my coordinate. Let's call them maybe X, Y, and Z. So based on these three coordinates, again, this is a rigid body. It can have 6 degrees of freedom system. But let's say when we put it on these 4 springs, we are only interested in its motion moving ups and down. So I would say it has 1 degree of freedom going ups and down. So let's call that one Z, like the variable that we are going to discuss. It can rotate about X. So let's call that one maybe theta. And also it can have a pitch or rotation around Y as well. So let's call that one maybe phi, or whatever angle we want to call. So we say this system has 3 degrees of freedom system. So it is a 3 DOF. So the question define it for you. Sometimes you need to decide how many degrees of freedom system like your system has. Maybe the same box here. You are analyzing, let's say, a system that you are interested in its motion in Y direction. So that adds another degree of freedom system for you. But for now, let's say I have this machine, I put it on a table. I'm just interested to know how much it moves ups and down, how much it tilts, and how much it, let's say, create a pitch rotation for me. Theta, phi, and Z. Right? Now the same system, if I add, let's say, a spring on top of it, let me use another color. Let's say I add another spring over here. And on top of that spring, I will add another mass. Let's not make that messy. I'll just copy that things. Bring it down here. So let's put now a spring on top of this. And we put another mass. So this is M, and this is, or let's call this one M1, this one M2. Okay, so picture is not very clear. Let me try it again. Maybe if I get rid of that thing. That thing. So let's, where is my pen? So we put a spring on top of this box, and then there is this another mass sitting on top of that spring. So this is M2 and this is M1. Right. So originally our system had 3 degrees of freedom system. Now we add another mass on top of that, and let's say that mass, we are only interested in its motion going ups and down. Let's say that's only a particle, and I'm interested only knowing how much it moves ups and down. Call that one maybe, so Z2. And this one, let's call that one Z1. So now my system has 4 degrees of freedom system. So it is a, sorry, 4 DOF, or 4 degree of freedom system. All right. So that's easy. You can just checking the system that you have, make sure that if you need to consider it as a rigid body, like this big box, or if it is something that you can consider it as, let's say, like this M2, as more like a particle. Maybe, let's say in your car, the whole car is a rigid body, right? Because the car can move ups and down, it can tilt, and it can have a pitch. But you sitting in your car, if you're analyzing your own vibration, you can assume that yourself as a particle. Okay, so this is how it goes. On your note, you have like this car, which we can quickly check with each other. Now you should be able to recognize how many degree of freedom system it has. It's a classic problem. Most of vibration analysis for car start like with this system. The way it goes, usually we model tires as springs. So these are tires. So each tire acts as a spring. It has also damping. So in more accurate model, later you will see we add also damping for tire. But tire by itself is a spring. So this is the mass of the tire. So tire model as a spring. So this is the tire itself, whatever weight it has with the wheel inside and everything, right? And then of course, the tire hasn't been connected directly to the body, right? Unless it is 300 years ago, those cars, no chassis, right? They have all damper and system. So this is the like a model, a simple model for a car vibration. So looking at this model, you can say, well, I have the vibration going ups and down. So that's one variable, right? We call it X. The whole car moves ups and down. So I have the phi angle, the pitch angle. The car can rotate around like that axis. I have theta. So on the side, you can see theta as well. And center of gravity, it can move like, not that one. Center of gravity can move ups and down. So that's the side view. Front view, you can see X. And you can see also this phi angle. So that's just for the car. So the car itself has then 3 degree of freedom system. It can go ups and down, right? It can have this phi angle, let's call it a pitch, and it can have this tilting, right? So on the side, we call it theta. We have 4 tires. The tires, we can treat them as particles because their rotation, let's say, in terms of vibration, doesn't matter. So I have 4 tires. Each of them, they are independently moving. So in total, I have 7 degree of freedom system. So for each of them, and let's call this one, for example, this tire, let's call it maybe X1, X2, and so on. So you have 2 other on the back. So this system then gives me 3 degree of freedom system for the body, which they are X, theta, and phi, and 4 degree of freedom for tires, which they are like X1, X2, X3, and X4. So it is a 7 degree of freedom system, which actually you will do a project. Your final project is on this system. Now, you've learned before that like in single degree of freedom system, when you have a system, it's going to be subjected to some external loads, right? So those loads can be some harmonic force, or they can be base force, some rotation. So in a car, of course, you have the engine rotates, creates some harmonic force. Also, the car is on a road, so it can have base motion. So this is one base motion. On each tire, for each tire, right? This base motion, in fact, it is a road. You put the car on a road has ups and downs, it's not flat. So create some base motion for you. So you will see there is no difference between this model and the single degree of freedom system that you've learned before. Most of the concepts, they are the same, except now, instead of having just one equation, you have to deal with 7 equations. Instead of having 1 frequency, you have to deal with 7 frequency, and so on. Okay, so and our objective again here in this chapter is learning how to solve n degree of freedom system. N can be any number bigger than 2, bigger and equal to 2. Because if it is less than 2, it is 1 degree. We already discussed it. N can be 2, 3, 4, 100, 1 million, doesn't matter. All the concept, everything that we say about 2 degree, it's correct about 1 million degree of freedom system. But again, as I said at the beginning, we will do only for 2 and 3 on the slides here, because I don't want to write a lot of equations. Okay, it takes a lot of time. More than 3 degree of freedom, usually we better use like MATLAB, because you have to deal with the matrix, inverse it, do a lot of work with it, and it's a lot of work. It's just a headache. Okay, so here is our then the story that we want to do. Okay, we want to analyze n degree of freedom system, but we will focus on only on 2 and 3. Any question or concern before I start discussing this chapter? Yes.
So the base motion doesn't count as extra degrees of freedom?
No, that's just external, let's say, excitation, right? Remember, for 1 degree of freedom system, you have the same. When we have a 1 degree of freedom system, right? You said you have the base motion, and this is x. You consider it as a single degree of freedom system, SDOF or 1DOF, right? So the base, no, this is the excitation. And each of them, of course, has its own excitation, because when your car is on a road, each point has different excitation. It might have same or may not. So let's then start with the simplest possible model. 2 mass on top of each other, they're connected with springs. M1, M2, K1, and K2. So very similar to what we did for single degree of freedom system. Let's do a quick recap. For a single degree of freedom system, what we did, first, we modeled them. By modeling, we mean we derive their equation of motion. We have 2 methods, right? Newton's and Lagrange. So the equation of motion. Then we attempt to solve them, and we try to find what this system will do if we just excite it naturally. We'll find its natural frequency. Then we add damping to the system. Then we add external excitation. We will do the same steps here, but for n degree of freedom system. Okay, let's do that. So I'm going to derive the equation of motion. This is what we mean by modeling. We have 2 methods. Let's start with our friend Newton. So Newton's law. So for Newton's law, always we draw the free body diagrams. Let's quickly do that. It's easy to do. So this is, let's say, my first mass. That's my second mass. And I pretend that I move them, disturb them. And the same story, it is up to you to select your variables. Either they can be ups, down, one of them up, one of them down, doesn't matter. But you need to be consistent. When you show them on your schematic as that, you have to be consistent. For you now, x1 and x2, it is positive like that. Our start point similar to before, is equilibrium. So now you have two mass, they are sitting on top of each other, they had weight, and their weight creates some compression in the springs. So it means I don't need to be worried about the weight when I draw the free body diagrams, and I don't need to take into account the pre-compression in the springs. So then I will end up with a force here for the first mass, which that force has to be K2 x2 minus x1, because x2 went up, x2 compressed it a little bit. Action and reaction, the same thing goes for the other one. So that's going to be then K2 x2 minus x1. And over here, it's easy. It's going to be just K1 x1. This is our free body diagram. Then the Newton law says sum of the force must be equal to m acceleration. So I'll end up here writing minus K2 x2 minus x1 equal to m2 x double dot 2. And for the other one, I have K2 x2 minus x1 minus K1 x1 equal to m1 x double dot 1. So let's check to make sure no mistake here. So we have minus, and this is m2, and this is one is m1, and this is positive, this is negative. I rearrange them to make them looks a little bit better, and I will maybe write down the first one here, m1 x double dot 1 plus K1 K2 x1. I move everything to the other side, minus K2 x2 equal to 0, and then m2 x double dot 2 K2 or yeah, K2 x2 K1 x1 equal to 0. Okay, that's positive, that's negative. Okay. So this is our equations of motions, or differential equations of motion, which they are ODEs. They are a system of ODEs to be exact. Okay, make sure that I didn't make a mistake here. So this is then positive, right? Okay. This is x2. So instead of one equation, we have two equations. But if you take a look at these equations, you will see they are interconnected, right? In one of them, you have x1, x double dot 1, x2 in another one, something like that. And here is a terminology alert. And that is these two differential equations are coupled, right? They are not independent. You have like x1 in one, x2, one variable is affecting the other one. In one equation is affecting the other equation. So we say they are coupled, or they are connected. They are not independent. Yes.
The second of your equation, I think that would be K2 x2 x1.
So let's check the second one, m2 x double dot 2, right? Then I have K2 x2 All right, you're right. It is K2. K2 X1. Thank you. Yeah. So please correct this one. Make sure it is correct. You're going to have a lot of indices like that, so you have to make sure they are correct. So let's do the same things with Mr. Lagrange. Lagrange's equation. So Lagrange equations, we know it has a form d dt, derivative of t with respect to a variable. Let's call that variable q, qi, minus derivative of t with respect to qi, derivative of u with respect to qi, derivative of r with respect to q dot I is equal to qi. So that's our standard Lagrange equation. So for Lagrange, I need to find t and u. So t is the kinetic energy, right? I have two masses. First mass is moving with the speed x dot. Second one is moving with a speed x dot 2. So that's t. And I have potential energy. So I have spring 1, which deflects by x1. And I have spring 2, which deflect x2 minus x1 squared. So our Lagrange equation, right? Our Lagrange equation, now we can repeat it because we have two variables. We can have 10 variables, doesn't matter. So Q represent our variables. So first, we will do it for x1, right? So for x1, my equation, it will be d over dt, derivative of t with respect to x dot 1 plus derivative of u with respect to x1 is equal to 0. So I didn't write the rest of them because they will be 0. Right? We don't have any external load. We don't have any damping. And this term t, of course, in t, we don't have any x. So when we take the derivative, it will be 0. So let's take the derivative and see what we will get. If I take the derivative of this one, derivative of t with respect to x dot 1 gives me m1, right, x dot 1. Derivative of t with respect to x1 gives me k1 x1 plus k2 x2 minus x1. And then derivative of inside bracket gives me a negative, so it's going to be minus that x. So if I summarize everything, I will get from here, I would get m1 x double dot 1, right, plus k1 k2 x1 k2 x2 equal to 0. That's my first equation. Right. I need more room, so we repeat it for the second equation for x2. So you know the drill. We'll get m2 x double dot 2 k2 x2 minus k2 x1 equal to 0. So same equations, in fact, which this is what we expect, right? So we get the same result this time without free body diagrams, this time by just taking the derivatives. Sometimes it makes sense to use Lagrange, sometimes Newton law, and they are always correct. So in your midterm, some of you tried for question 2 Lagrange equation, but what you missed was this term here. This term wasn't 0. Maybe I post a solution because some ask how we can solve the midterm question with Lagrange. Yes, you can, but you have to be careful that that particle has two motion. Anyway, not get confused by that. So we can find then the differential equations of motion for a 2 degree of freedom system using the two methods that we learned before. We ended up with a system of differential equations. They are usually coupled. If they were independent, then it means there is no relation between these two variables, and it was more like a single degree of freedom system, each of them. Usually, it's better to work with when we have a system of equations, write them in matrix format. So, but we don't have to. Usually, it's better. So in matrix format, these two equations will look like M1, 0, 0, M2, X double dot 1, X double dot 2, plus K1, K2, 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 and K2, no, K1, to see K2, that's right. X1, X2 equal to 0. So they are the same equations, I just write them in matrix format. So if you multiply these matrices, you have to get two equations exactly the same. Let's quickly check, make sure that I didn't make any mistake. So M1, M2, K1, K2, K2, and yes, seems okay to me. But you always can find something. All right. Any questions so far? Seems easy. Okay, right? So this is just a matrix format of what we have before. Now, if we pay attention a little bit to these matrices, we can see we have a matrix of masses and a matrix of stiffness. Okay, so these are matrices, and then we have vectors of acceleration and a vector of displacement. So in other words, I can write down like this equation as m. Let me write it down here. I can write them as m x double dot plus kx equal to 0. Same equation that we had before, just instead of a mass and a stiffness, we have a matrix of mass and matrix of a stiffness. The form is exactly the same. So two terminology alert here. Terminology. Because we are going to use them a lot later. So take a look at the mass matrix. The mass matrix, if you look, it is a diagonal matrix, right? Only on diagonal you have numbers, the rest are zero. So we say that in this system, masses are decoupled, or the mass matrix is decoupled. Mass matrix is, we say it's diagonal. So, but take a look at the system itself. Remove the stiffness. Imagine there is no spring. Does these two systems have any effect on each other? Let's say there is no spring. X1 and X2, they can independently move, right? So we say if we remove springs or these springs here, these two mass or the motion of these two mass has no effect on each other. Have no effect on each other. Okay. So you remove the springs. These two are independently can move. They have no effect on each other. And when that's the case, then definitely your mass matrix should be diagonal. Should be zero everywhere else other than diagonal. Otherwise, you make a mistake here. Just as a test, if I give you, let's say, this, let's say I have maybe a cart, and this is on a wheel. And then let's say on top of it, I have let's say a wheel. Okay, so I have a car, then I have a wheel on top of it. So this rotate with theta, and this one is moving with x. So there is no spring between them, but you can visualize these two should have an effect on each other. For example, if you move x very fast, maybe the disk rotates faster backward. We don't know yet, but this is something that we can guess. If there is no spring between these two, maybe x and theta, later when we develop their matrices, their mass matrix, maybe their mass matrix will not be zero over here. I don't know yet, we will see later, okay? But just as a quick test, you remove the springs, you just check to see if these two have an effect on each other. If you got non-zero here, it means you made a mistake here. So let's go back to the same things that we had here. Now let's take a look at the stiffness matrix. Stiffness matrix. So is it diagonal? No, it's not. So again, we say, let me make this thing small. I need more room here. Next time I should create 2 slides for this one. Not a good estimation. So that's one thing. Second things that we need to pay attention, the stiffness matrix is coupled, or it is not diagonal. Now, a fact that we can check is look at the system and move x1 and x2 and see if, for example, if you move x2, so the deflection of one spring is going to affect the other one. So on this simple system, it's obvious, right? If I just move the top one, probably is going to move the bottom one with him as well. So these two have an effect on each other. They are connected, we say. Okay? Or there is a spring that connects x1 and x2, and that spring is K2. If you have a system that does not have K2, then you would say that these two variables are not connected. But here you will see there is something that connects x1 and x2. So we can write here, there is a spring. And that spring, it is K2. Connects x1 and x2, right? This K2 is connecting these two variables. Now, what do you have on your off-diagonal matrix? So this is the diagonal. On off-diagonal, what you have is minus K2 minus K2. Because you have K2 connecting these two variables. And on your off-diagonal, you can see K2. Of course, you don't need to check any of these because math will find it for us. But it's important to have a sense what's going on and also a quick check to make sure that we derive the equations correctly. And last things that I want your attention is take a look at on the diagonal parameters. Let's just focus on one of them, on the first one, K1 plus K2. So which springs are attached to x1, or which springs affecting x1? It is K2 and K1, right? K2 and K1, they attach to this x1. So, and you see we have K1 plus K2. What about mass 2? For mass 2, it is only K2, right? Mass 2 or variable x2, it is only K2 that attached to it. It's not K1, right? K1 is far away, it's somewhere else. So let's also add that one, and then we'll be done for today. And what I would write here, the off diagonal or sorry, the diagonal. Diagonal, we talk about the off diagonal. The diagonal elements are the sum of stiffness attached to each variable or to each mass. Okay? So let's summarize. We had a 2 degree of freedom system. We used Newton's and Lagrange method. We ended up with 2 differential equations. We said these 2 equations are not independent. They are coupled. They are connected, right? And then we write them in a matrix format because it's easier to work with them. And we look at their matrices. So we have a mass matrix and we have a stiffness matrix. We look at the mass matrix. It is diagonal. We say mass matrix is decoupled. or these two masses, their acceleration maybe are independent without these springs. Then we look at the stiffness matrix, right? We got some information. First of all, we realize that it's not diagonal. The off diagonal, they are negative. Okay, so if you got positive, it means you solved later an equation. You got positive, it means you made some mistake somewhere. They are negative. And what is their value? Is the value of a stiffness connecting these two variables, right? Right here, x1 and x2, they are connected by k2. And the diagonal one is the sum of a stiffness that attach to each variable, okay? So again, we let the math to find this for us. This is all just fact check to make sure our equations are correct. So assuming that we know how to derive the equation of motion, our next topic is what we need to do with these equations. We need to solve them, right? Which is the next topic. See you on Friday. Thank you very much.